Hello students, welcome back to another lecture of our course Environmental Modeling and Simulation. In today's lecture, we are going to continue our discussion on bifurcations. And in the previous lecture, as you remember, we looked at examples of saddle node bifurcation in 2D systems. And in this lecture, we are going to look at example of supercritical pitchfork bifurcation in 2D system. We're going to look at one of the easiest system we have. So, if you remember, one kind of bifurcation that we started in 1D looked something like this. dx by dt is equal to ax minus x cube. And as we varied the value of a, the behavior of the fixed points changed. Now, to make it 2D in a very simple 2D model, what we can do is add a second variable and keep it very simple, minus y. Now, this is a 2D version of the same bifurcation. So, the first step that we want to do is we want to understand how, as we vary the a, the fixed points are changing. And if you remember, very easy to find out the fixed point here, dy by dt should be equal to 0, and separately dx by dt should be equal to 0. In our step 1, we need to find the fixed points. So, basically ax minus x cube needs to be 0. So, taking x common, a minus x square should be equal to 0. Now, you can see depending upon the value of a, this will have 1 or 3, or in one particular instance 2 values of x when dx by dt will be equal to 0. X equal to 0 is always going to be one of the fixed points. The other one we are going to get are plus minus root a. Now, if a is positive, we will have 2 fixed points. If a is 0, we will have, this will become 1 fixed point, and if a is 0, then this fixed point apart from x equal to 0 will be non-existent, and then we will have only 1 fixed point total. Now, if we look at our second equation, dy by dt is equal to minus y is always going to be 0. So, let us start with the simplest situation when a is less than 0. So, when a is less than 0, we have just one fixed point, which is 0, 0, and we want to understand the behavior of this fixed point. So, to understand the behavior of the fixed point, we can either use the null-Klein method or we can do the characteristic equation. Now, this is a very simple model. So, characteristic equation method is going to be very easy. So, let us just go ahead and use that. Typically, it is for the more complicated systems or systems that are more calculation intensive that I like to use null-Kleins first. Okay, so let us find out the Jacobian. Now, treat this as f and treat this as g, and then the Jacobian is very easy to calculate. So, this is our Jacobian at j 0 0. When a is less than 0, we are going to get our characteristic equation would be 0 a 0 0 minus 1. So, this is when there is only one fixed point, it is 0 0. This is our characteristic equation. Tau is equal to a minus 1, delta is equal to minus a. Now, remember a is negative, so tau is going to be less than 0. Now, also remember that delta is equal to minus a, which means delta is going to be positive. So, our tau is negative, our delta is positive, we are in the fourth quadrant. So, if you remember what is in the fourth quadrant, and by the way, the graph I am referring to when I say fourth quadrant is tau versus delta diagram, where here we are dealing with saddle nodes on the left side in the second and the third quadrant. In the fourth quadrant, we have stable systems. In the first quadrant, we have unstable systems. And then here we have centers. On y-axis, we have non-isolated fixed points. Okay. So, we are in the fourth quadrant, so we are in the stable zone. So, either now 2 possibilities are there. If we are under the curve of tau square minus 4 delta, we are dealing with stable spiral. If we are outside tau square minus 4 delta, which means tau square is greater than 4 delta, then we are dealing with a stable node. Tau square minus 4 delta will be given by a minus 1 whole square minus 4 delta, so it will become plus 4 delta. So, this is the situation when a is less than 0. Now let's look at the flow lines around this stable node. Remember that the flow lines will be tangential to the slower eigenvector. So the next step would involve finding out the eigenvalues, finding out the eigenvector, and we really don't need to go through it to understand how this bifurcation happens in 2D systems. So I'm going to skip that. I'm going to just tell you that this is how it looks like. But by the way, if in exam I ask you to find the eigenvectors and eigenvalues, and in real life when you do need to find them, please remember how to find them. For that you need to take your characteristic equation and then remember determinant a minus I lambda is equal to 0 to find out the lambda values, and then a minus I lambda into eigenvector equal to 0 will give you eigenvectors, and then you can draw your phase portrait. Okay, now let us see what happens when a is equal to 0. When a is equal to 0, then now our fixed point is still just x equal to 0. We have only one fixed point, so the behavior remains quite similar. Another scenario where a is greater than 0. Now when a is greater than 0, two new fixed points emerge, which are x is equal to plus minus root a. Now let us see what happens when we have two new fixed points. Once again we are going to use our Jacobian. Now we have three fixed points, and then the first fixed point is of course x equal to 0. We will have a very similar tau in delta, it is going to be a stable fixed point. The next fixed point is going to be plus root a and minus root a, y is equal to 0 in both cases. So let us look at what our Jacobian looks like at plus root a 0. A minus 3a 0 0 minus 1, we end up with minus 2a 0 0 minus 1. Now let us look at our tau. Tau is minus 2a plus 1 and determinant is 2a. Now in this scenario remember a is greater than 0. So when a is bigger than 0, determinant is going to be positive. So we are definitely not dealing with a saddle node. Now let us look at tau. Tau is going to be interesting. Tau is equal to minus 2a plus 1. So a is positive. Now if a is more than 1 by 2, then tau is going to be negative. If a is equal to 1 by 2, then tau is going to be 0. If a is less than 1 by 2, then tau is going to be positive. So now we have three scenarios here. So a bigger than 1 by 2, as I said, would be tau would be negative. So tau is less than 0, tau is equal to 0, tau is more than 0. Notice one thing, delta is positive. So once again returning back to our diagram, returning back to our tau versus delta diagram, delta is positive, so we are dealing with either the first quadrant or second quadrant, definitely no saddle. Now if tau is positive, then we are dealing with the unstable quadrant, which is the first quadrant. Now tau will be positive when a is less than 1 by 2. When a is equal to 1 by 2, we are dealing with the center, and when a is greater than 1 by 2, then we are dealing with unstable situations. So we know here that as the a value changes, two new fixed points will appear. So this is a pitchfork bifurcation, and what we will see is that when the two new fixed points appear, the 0 fixed point becomes unstable, and the two new fixed points, depending on the value of a, will behave very similarly to the pitchfork bifurcations that we saw in 1D dimension. Now what I want to do is highlight to you that these bifurcations that we have studied so far, even in 2D, whether it is saddle node, pitchfork or transcritical, they have one thing common. At the critical point when the bifurcation happens, tau square minus 4 delta is equal to 0. Even in this scenario, in the example that we looked at here right now, it is this line that will determine whether the system goes from stable node to unstable node. The stability of the fixed point will be determined by where tau square minus 4 delta is, whether it is on the curve is equal to 0 or less than or more than that. So tau square minus 4 delta is equal to 0 tends to be often the critical place, the critical point for 2D systems, and it also can be multiple dimensional. Tau square minus 4 delta for 2D systems is the critical line. Now these systems where tau square minus 4 delta is equal to 0, they are very peculiar, and saddle node in 2D, transcritical in 2D and pitchfork in 2D, all of them lie in tau square minus 4 delta equal to 0 system of bifurcations. These are also known as zero eigenvalue bifurcations, because this is also when the eigenvalue, one of the eigenvalue becomes 0. So whether we are talking about saddle node bifurcations, or we are talking about transcritical bifurcation or pitchfork bifurcation in 2D systems, all of them are of a particular category where one of the eigenvalues becomes 0, or tau square minus 4 delta is equal to 0. Now we also have systems where this does not happen, and this is in the case of complex eigenvalues where they have imaginary portions also. These kind of bifurcations are a completely different class, and they are referred to as Hopf bifurcation, and they are very important in environmental systems and also in other fields like electronics, electricity and chemistry. But even in environmental systems, Hopf bifurcations are very important. Now, how the Hopf bifurcations work is, you need to understand they are relevant when we are inside tau square minus 4 delta curve. So, we are dealing with spirals, we are dealing with centers, we are dealing with oscillations. So, they are very important when we talk about oscillations. Now, you must know this from your training in environmental sciences, environmental engineering, or general knowledge about EVS. Several phenomena in environment oscillate, they cycle, whether it is weather pattern, levels of different contaminants in the environment, or life cycle in itself, nutrient cycling, all of them cycle. So, mathematical way of expressing the cycle is oscillation. Now, the oscillations may damp down, which is when they are spiraling in. They might become more and more pronounced when they are spiraling out, or they might stick to a closed orbit, in which case we might have a center which is non-isolated orbits, or we might have isolated orbits, which is in case of limit cycles. So, Hopf bifurcations are almost always associated with oscillations. Now, two things are possible. Let us say we have an oscillation that starts, an aberration or an oscillation that starts, and it goes like this and then it dies down. Now, this can be an example of Hopf bifurcation. Now, this dying down is happening as we are changing the parameter. Let us call the parameter mu, the parameter in question. There was an oscillation happening, we started increasing or decreasing the value of mu, and the oscillation died down. So, we went from oscillations to no oscillation. We went from complex eigenvalues to real eigenvalues. The other possibility is that we have an ongoing oscillation, and as we change the parameter, they become more, the amplitude changes. So, not so dramatic, I mean could be dramatic, but I don't want to make them discontinuous, but the amplitude changes. So, these are the different kinds of oscillations and bifurcations that we see under this category of Hopf bifurcation. I am not going to go much in detail about Hopf bifurcation in this course, but I am going to give you some examples and show you how they work. So, let us try to understand how Hopf bifurcations behave. So, let us say we are looking at the first example where we have oscillations and then the oscillations are disappearing. So, the bifurcation may move in this direction or it may proceed in this direction. Either way, what we are noticing is that if we draw our eigenvalues, and let us say the imaginary portion is on y axis and the real portion is on x axis, when we have complex conjugates for our eigenvalue, when there is oscillation happening, we have a non-zero imaginary part, and since it is dying out, in the example that I am looking at, we have oscillations and then they are dying out, they are reducing in amplitude. So, the real part has got to be negative. So, we know that we are in the second and the third quadrant. So, let us say our eigenvalues look like this. They are dying out, they are going from complex with the negative real values to positive real values. So, what needs to happen for these kind of bifurcation is these two eigenvalues need to move here. They need to either let us say get rid of the imaginary completely, like in the case of the example here, the A will have a real eigenvalue. Other possibility in Hopf bifurcation is that we do not have imaginary values, we have real negative eigenvalue, and then it again skips to the right. Typically in Hopf bifurcation, it is the skip to the right side of this diagram or from right to the left side of this diagram that we cover. Now, Hopf bifurcations can also happen when we change the stability of our oscillation. So, let us say we were a stable spiral And then from stable spiral, we went to an unstable spiral. If you look at a tau versus delta diagram, and this is a tau square minus 4 delta curve. So what's happening here, going from stable to unstable bifurcations. So we are going from this region, which is a stable spiral region, to an unstable spiral region, which is here, by changing one parameter. It's also, the other way movement is also possible, that we go from an unstable spiral to a stable spiral. Remember, stable spiral means we are moving closer and closer to the fixed point. So basically the amplitude might be reducing, and but the periodicity of the oscillation may or may not change. And unstable spiral means now we are blowing out. Now we have already seen something like this happen in the previous example. If you change the value of A, your bifurcation may move from stable node to stable spiral to unstable spiral, and then unstable spiral to stable node, or in either direction. All of these will come under Hopf bifurcation. Another feature of Hopf bifurcation is that the oscillations tend to reverberate for some time before dying out. In colloquial terms, we call it ringing. The oscillations ring for some time before they die out, and we know this from damped oscillators. They oscillate for some time before the oscillations stop. We know this from damped oscillators, and especially exponentially damped oscillators, which is a kind of damped oscillator, come under Hopf bifurcation. In next lectures, we are going to look at some examples which will follow the Hopf bifurcation, and we will look at more in detail through examples. So this was a very brief introduction to Hopf bifurcation. I don't want to go much in depth here, but please understand, when we are dealing with complex eigenvalues, so complex conjugates of eigenvalues, and then they are changing their stability, like unstable spiral to stable spiral, or oscillation to no oscillation, or no oscillation to oscillation, or even changing from, so let us say spiraling in to spiraling out, even all of that are covered under Hopf bifurcation. Okay. Now in the next lecture, what we are going to do is we are going to go back to our insect outbreak. If you remember, insect outbreak was kind of a pitchfork bifurcation with imperfection factor in it. We are going to go back to that model, but with a difference. We are not going to focus on the insect population, we are going to focus on the health of forest. So to give you a brief overview of the next model that we are going to look at is health of forest. And it will depend upon two things. We are going to use two factors to determine it. The first one would be tree cover. So how much forest cover we have. The second factor is going to be the total amount of energy that the forest has. Now E energy, it sounds like a very subjective term, but basically it tells me how much diversity, how much biomass, how healthy the forest is, how much trees can it support. If the forest is not healthy, it can't support a lot of tree cover. If the forest is sick, let's say there's a fungal infection or some kind of insect outbreak, then the health of forest goes down. We are also going to continue sticking with our spruce birdworm. That was the insect we used in our insect model. We are going to stick with them, but we are going to use them as a parameter. As we vary the number of birdworms, how does it impact the health of our forest? How does it impact the tree cover? And then we are going to do the bifurcation analyses. I'll introduce you to the model very quickly, and we can look at the interpretation of the parameters in the model. So the model looks like this. Okay, so change of variables here. S is representing the spruce tree cover, because we are talking about spruce birdworm. So S is telling me about the tree cover of a particular kind of tree in the forest. E is the energy of the forest, it's the health of the forest. The higher the E, the more trees it can support. The higher the E, the more resilient the forest health is going to be. Now if you look at this system, ds by dt should remind you of something about logistic system. So here we have the exponential growth rate. Here we have a logistic term which is telling me that the forest can support only so much of spruce tree cover. So the spruce now trees cannot continue increasing in number endlessly. Then we have Ke by E, which is dividing. So S by Ks is the limit on the maximum number of spruce trees that the forest can bear, and then E by Ke, which is health, the limit of the health of forest. Forest can't get healthier than that, cannot sustain more life than that, is also a limiting factor for the maximum number of spruce trees. So this is very interesting, and I definitely want to dig into more in depth into what's happening here, why we are multiplying these two limiting factors, why S is on numerator and E is on denominator. In dE by dt, which is again talking about the fitness of the forest, we again have an exponential growth term, and then we have what appears to be a limitation, that the forest cannot continue growing indefinitely. There is a limitation of other resources that forest requires, like the water cycle, nutrient cycle, and also the land cover available on the earth. And then we have this very interesting term here, minus Bb by S. S is talking about spruce cover, and B here is the population of the insect, birdworms, spruce birdworms, which eat up the spruce tree leaves. And in the next class, we are going to go in detail about this model. We are going to look at the kind of bifurcation this model has, and we are going to interpret it and understand what this model tells us about the health of the forest, its relationship with the spruce tree cover, and the amount of insects. All right, that's all for today, and thank you.